Now we're going to talk about something a little bit different, binomial distributions. And this is a discrete distribution based on binary outcomes, yes, no, success, failure, something that you can designate with two different outcome levels. So we often call these success or failure, but it's arbitrary what you call success. The idea is that the probability of success has to be the same for all trials or rounds of the event, and the trials are independent. So success on one doesn't change the probability of success on the other, and we denote X as the number of successes in N trials. So here's an example, how I almost lost Bonnie in China. I was leading a group of MBA students on a study abroad trip in China, and there were a number of them. Some of them were international travelers before, um, and they were there to learn about some companies that were doing business there and also learn about culture. So I'm going to actually define success as venturing out on their own because I think it's a good thing to get off the beaten path sometimes and not have everything scripted for you when you're studying abroad. Um, so we're going to define that as success. And staying with the group all the time, we're going to designate as failure, despite the fact that them taking off independently did possibly cause me to have a heart attack. Anyway, the probability, these are graduate students, so the probability that any given one will venture out on their own is pretty high. I assigned it a 77% probability. Um, and so one night, Bonnie did actually go wandering off, and we couldn't reach her because we didn't have good cell phone service at that point in time. This was a number of years ago. And we spent a few hours anxiously waiting for her to return, and she did, so that was good. Um, but she was one of three of them that tended to be kind of adventurous. So we'll talk about them more in a minute. So the binomial distribution has two parts to it. One is the number of ways that you can get X successes out of N trials. And the formula for that is n factorial divided by x factorial times n minus x factorial. Recall that factorial means you take the number and multiply it by the next lowest number, and then the next lowest number, and the next lowest until you get to 1, and then you're done. So that's one part. And then the second part is the probability of success on N trials. So that is like a joint probability, like we've done with probability trees. So it would be like success and success and success and however many of those, and then the rest of them being failures, which can be anywhere from 0 to all of them being success or being failures. So that is the probability of success raised to the x power, so the number you're looking for, times 1 minus p to the n minus x. So notice how the pieces in the first part of the formula fall into the probability part as well. So, for example, here are three of my travelers, Bonnie, Mel, and Kate, who definitely were kind of adventuresome. And what is the probability that two of them will venture out on their own? So we want the number of outcomes providing two successes out of three trials. Okay, so n is 3 and x is 2. And so that is 3 factorial over 2 factorial times 3 minus 2 factorial. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. 1 factorial is 1. By the way, 0 factorial is also 1, and that is 3. So there are 3 different ways that 2 of them could have gone out on their own. It could have been Bonnie and Mel, or it could have been Bonnie and Kate, or it could have been Mel and Kate. Okay, so there's 3 different ways that could have happened. Um, So what is the probability of any combination, any one of those three combinations? The success probability is 77%, 0.77. So the failure probability is 1 minus that is 0.23. And so if Bonnie and Kate do venture out and Mel does not, that's 0.77 for Bonnie times 0.77 for Kate times 0.23 for Mel, and that is 0.136, okay? Or if we put it in the formula, 0.77 raised to the second power, because we're talking about two of them taking off, times 1 minus 0.77 raised to the 3 minus 2, which is 1, okay? And that gives us, again, 0.136. You can also do this as a probability tree, right? So we've got Bonnie, who ventures out or stays. We've got Mel, who ventures or stays, and Kate, who ventures or stays. Okay. And so the paths that have two of them are this one: Bonnie goes, Mel goes, Kate stays. Or this one: Bonnie goes, Mel stays, but Kate goes, right? Or this one: Bonnie stays, but Mel goes and Kate goes. And notice that the probabilities at the end of all three of those are 0.136. Okay. The probabilities round to 101%, but don't worry about that. That's just a little bit of rounding. So the full function puts both of these pieces together. So we have the number of successes, the probability of successes, the number of ways we can have the X number of successes, and the probability of that particular type of combination. So in our case, we had 3 ways that we could have 2 successes, and the probability for any of those was 0.136. So 3 times 0.136 is 0.408. The binomial also can be approximated with a normal distribution. So the expected value is the mean, and that is n times p. So the number of trials times the probability of success. The variance is n times p times 1 minus p. And the standard deviation, of course, is the square root of the variance again. So suppose we took 6 students to China. How many would we expect to venture out on their own? Well, the expected value is n times p, so 6 times 0.77, so 4.62 we would expect. The variance would be that number times 0.23, which is 1.06 down here. Okay, and the standard deviation is the square root of 1.06, which is 1.03. In R, it's pretty easy to get the probability of exactly n successes in capital N trials with success probability p, and I've switched notation just because this is the standard notation in R. And so you use D binom, and then the little n is like our x, is how many successes. The big N is like our n, so it's how many total trials, and then the probability is p. So in our example of 2 out of 3, we do D binom, 2, 3, and then 0.77. Remember to put that probability in decimal format, and that gives us 0.409, which is very slightly different. We got 0.408 before, but that's just due to rounding when we did it by hand. Phew, that's it for this chapter. Let that all settle.